to become familiar with, the idea is to use something like the morphologic mapping as a way to get started. And in a sense, it's really a means to the end, which is the final mapping product, but it forces you to look around the area, and it should be pretty easy to read the topography to identify these morphological features, which are, as I said in my initial lecture, kind of the building blocks of our interpretation. So it's like the letters that make the words, that make the paragraphs, that help us tell the story of this place. And so morphologic mapping is kind of one, I think, pretty straightforward way to get started. And then from there, you can make interpretations that build more complex, semantically, products, which are like these ones at the bottom here: geologic map, morphogenetic map, process map, or hydrological. They all require higher degrees of interpretation. And so you would do them kind of subsequently. So this assignment had also another goal for the assignment was to get you kind of going in QGIS. So getting some of the key data in there and kind of getting some facility with it. And then the third thing is identifying these major tectonic landforms in this world famous place. And it's a place where we also have very high quality data. So just as a reminder of this kind of simplified mapping language, hopefully you found useful. And, it's not set in stone. You can see that some of the things that Savage GR had suggested in that original map, morphologic mapping kind of language, was a little more complicated, and some of it's kind of an ugly pattern. So, you may make some choices to make things look, better, how you want them to be. You just have to be consistent and systematic. And you may want to add features. So like I ended up adding this pattern, broad sloping surface, arrow points downhill. Okay, so here's the site. I tipped it on end, and in the interest of time, I kind of just focused in the central zone here, but hopefully you looked everywhere as we had requested. Also, in the interest of time, I did this with tracing paper on my desk rather than clicking it out, just so I could get something to you, given a little bit of time pressure I was under the last day or so. So here's kind of my answer, such as it is. So this is kind of a minimum product. But what we can see is the main features. Like I kind of started in the Northwest and worked my way along this central zone of kind of the most complex topography. And what I want to try to also use as I'm talking is to minimize interpretation. So I'm just looking at these morphologic features that I identified. So up here in the Northwest, there's clearly this ridge that's kind of bounded fairly sharply by this slope. And then there's basically a closed depression over here under the B4 symbology. So I showed that as the railroad track, which is the ridge crest, with then this concave up. Sorry, it's so concave up means, sort of the opening goes up if you look at it in 3D. So concave up slope break. And then as I come along, there's a couple of important little drainages right in here, these little troughs that actually are an important part of the story ultimately, even though they don't look like much. And then this through going channel here. And then above, I see this big broad slope, and I didn't really know what to do with it, but I didn't want it to be blank. So I was like, well, let's just, invent the symbol that's kind of the broad sloping surface. And again, this is a key landform, ultimately part of our story. So as we go along, we see this kind of a little bit of, sort of discontinuous features, but then we get to this really prominent curving valley. And so there, the way I handled that was to kind of map the upper slope break, that's a convex slope break, to the concave slope break, these paired breaks, and a little bit of a ridge next door there. And then as I go along, there's another ridge here. Did I get that? Yeah, I mapped that guy. And as we go along, this is a continuous, very smooth surface that curves into kind of parallel to the main zone of interest. And its boundary on especially this lower side is lost, but it's still bounded on the upper side, which is the northeastern side, by a slope. The contours, you know, here, this slope is not as steep as some of the other contours. So maybe that tells us a little bit about the history of development of this feature. Again, we see a couple of converging troughs on that surface and a broad sloping surface, you know, so not a lot in here, but notice I tried to not leave it blank. Actually, I sent a draft to our instructor, Dr. Scott, and she challenged me to not leave any blanks. So I went back and added a few things. So then these kind of three drainage, these troughs here are pretty straightforward to map, but one thing I didn't know what to do with, I didn't do much now, but you see they have a little bit of a flat bottom valley. So there's a little bit of aggradation probably that has occurred in them, but this is more of an interpretation. So now let's keep going. So kind of the most important, most prominent set of morphologic indicators is around this feature. And so what we see is a fairly deep, narrow valley that's basically indicated morphologically by these paired slope breaks, convex to concave, relatively flat bottom. And in some places, and this is important, right? In this area here, where it's kind of a more complex slope. And also we see it in this one where basically we come in and this upper relatively smooth part of the slope is quickly transitions to a steep one. So there's like a segmented hill slope. And then as we come into this area, you see it's flat, goes down a slope, and then there's a bench, and then it goes down another slope to the bottom. So this is actually a really key part of the story morphologically, even though it's kind of a modest little thing. So we don't want to miss anything, and that's why it's kind of important to have this steady level of mapping scale, that we're not, you know, sort of going past little things, which ends up actually maybe being important, but we miss them. So that's the main feature. And so I tried to show those paired slope breaks, but it's more complex here on these hill slopes than the rather simpler hill slopes to the northwest. So then the final part of this landscape is an important one, where we see this this scarp here, and it's kind of like the width of the scarp it increases as we go to the southeast, and also the drainage, the troughs on this scarp become more substantial as we go to the southeast, and the slope becomes a little less steep. And actually that's important, but it's a very sharp basal break, in a base, you know, concave up break. And then another thing that's very subtle, and I think many of us wouldn't have noticed, but is these little troughs on that down the lower side. And so you see the troughs here. And what's interesting is actually some of those troughs don't actually continue up to the scarp in a continuous way. That's actually ultimately a huge point or interesting problem that we can interpret. And so anyway, that's kind of the morpho map with the kind of a narration from me. So any comments or questions? Any things people had? Actually, and one thing I cut off, I'm sorry, one last thing to add is it didn't show up there, but this zone up here, there's another kind of weak scarp up at the top, and I won't say too much about it now, but the point is we don't want you to think that there's only, you know, kind of the middle of the map zone is the most important. There's sometimes can be features on the side which might be like ultimately interpreted as secondary structures. So any questions, comments? Chelsea, any commentary?
What are some of the things you look for to
Oh,
distinguish drainages from troughs?
sorry, I didn't see the chat there. Okay, drainages from troughs. So good question. It's kind of a again, being systematic, it's sort of in the eye of the beholder. So the trough. So I'm using this pattern, these this line with the little X through it as a basically a trough. So it's a concave up piece of topography, but it's pointed downhill one direction. So that's what this arrow means. So it's kind of a weak drainage, right? So if there was more coherent topography that would show that there was kind of probably likely continuous flow through there, I'd call it a drainage. But these little troughs are, we don't know what they are. They might not actually convey much runoff. But where I've tried to show, where the bigger dot dashes are is more continuous drainage features. But these little, kind of crenulations in the topography, I don't want to miss them, but I don't want to call them drainages either. So it's a little bit of the degree of drainage coherence, I guess. So a question from Christy, are these just the most sharp slope breaks? I got into the weeds finding more subtle ones. Yeah, so this is really more of I think key thing when we're mapping is using a consistent map scale, because you could get way in the weeds, and you can in our QGIS where you're like zooming all around, right? So one key thing is to fix your scale, your working scale. So don't let yourself zoom that much. Just kind of decide, I'm going to divide this into 20 little panels. So I'm going to fill each of those panels, my screen with it. And then what's that scale? Like 1 to 1,000. Do not change the map scale. Just go then across the area. And that will tend to give you a kind of a more even information density. And the other problem, in a sense, is this is a LiDAR derived digital elevation model. And so we're seeing some high frequency roughness that's coming from vegetation. And so that's something that we basically ignore in general. But there are some subtle things that end up being actually ultimately interpreted as anthropogenic. So this thing is a trail, but you see how there's little zigs in the contours. And there's also a road down here. It's just off of my screen that we pick up. But so I identified those in my I identified the trail in my morpho mapping as a little scarp right here. But so anyway, I guess I don't know if that totally answers the question, Christy. It's just uniform level of detail. And so I would just, if you felt like this was too sparse, then I would go back, but at a higher level of detail. So this is me sitting at my desk, kind of with tracing paper on 8.5 by 11 piece of paper. So this is what I get for level of detail.
One approach would be to kind of start at this, I think it's a fine detail, but maybe coarser, and we put a half an hour limit on somewhat intentionally. But once you do the course, to then dive down if you see more features. And I think for some of the later assignments, that would be a good strategy.
Yeah, and just so so maybe I'm like old school somehow. So I did this, literally analog, right? And that there's nothing wrong with that actually. And you may find that for some of these things, if you're really stuck, you should print it out and do it analog. And then you could always scan your map, georeference it, and digitize it, rather than trying to go straight in QGIS with the creative mapping. Probably it's more efficient to go creatively, in QGIS, but you can always take a piece of paper. Let me see, we got a few ephemeral streams can flow underground, so they don't have to be topographically continuous. Yeah, that'd be another point with the troughs, is we'd have discontinuous troughs, which would be a manifestation of possibly an ephemeral stream. There was a question, Albie wants me to go back to the topo. Anyone want to draw on here things they saw?
Did you have a question, Ob?
Oh, did you want me to say something?
No, thanks. It was just while you were talking, I wanted to see that.
Yeah, this is the low budget PowerPoint sort of overlay, but not really. Other comments or things? So like I said,
at least by the top of the hour, I want to move on, if not earlier, to Rachel.
Yeah, okay, I'm almost done. Hold on.
Rich, I just wanted to point out one thing. On the farthest trough to the right side, if you look down to the bottom of Ramon's map, the contours, can you go back to the contours, Ramon?
Oh yeah, sorry.
Yeah, so right there where your cursor is, that farthest trough to the right, as you go down to the bottom of the map, there are some sort of crenulations in the topo line to the right and to the left of sort of the main channel, and those can become important too when you start trying to interpret geomorphic landforms and stuff like that. Yeah, like that. And then on the other side, there's another one, and they're not necessarily, you know, they don't go all the way up into the main zone. Yeah, like that and that. Kind of those features in there. There's sort of like a channel form in the topography, but they give you some indication of what that landform might be. So.
Yeah, this is a very good point, Rich. So there's a real transition in the morphology here. And when we make the interpretation, we'll be able to explain it. But you can see, you know, what looks like pretty uniform slope. You know, the contours are pretty also kind of smooth as we go on these surfaces. But we cross and there's sort of these bounding troughs right here of this next zone. And then here is kind of, again, a change in sloping direction. Here's another little trough here. But also you see a change in the surface roughness, the contours, even though it's just contours, you can see there's a lot more little specks, which is just mean the contours going around a bush, basically. And then in the center, of course, we have this, what is this little drainage, which is continuous from this one. But also if you look at the width here, this is a fair bit wider than this one. This is kind of a narrow little drainage. So let me just look. Chelsea's want me to, okay, a few more minutes. So I have a few slides of then the interpretation, but before we get to interpretation, I wanted to see if there was more discussion. Christy, you had another comment, or is that your hand raised from before?
I'm comparing the contour map that I made in QGIS to yours, and like I think I have the same contour interval. Is it 1 meter? But yeah, I'm not sure the contours are like on the same meter, if you know what I mean, because like I'm seeing things that look like slope breaks on my map that aren't as obvious on your contour map. I'm wondering, do they always zero at 0?
They should. I mean, you could almost always, you have like a called the base contour, so it's usually integer, you know, like something 0.0, and then you go up from there or down from there. Yeah, I don't know. I mean, this is also, you know, me mapping on the contour map, whereas a lot of times people might have mapped on the hillshade instead. I just felt like I wanted to really make sure people didn't forget about contour maps for this, because a lot of the original work was done on contour bases.
The contours were so key for looking where they're closely to broadly spaced, like really nice for locating that contour. But yeah, mine looks different than yours. So I'm thinking like if I just tweaking the contour interval a little bit really pops different features out. And
yeah, so, I'm pretty sure this is the 1 meter.
So
go
Tamara thinks that this is ½ meter, and caution for QGIS, it does suggest an interval for you, and it's not always a meter, so you do need to pay attention to that.
Yeah, I just set it at 0.5 and it came out at whatever this is. It looks like this.
Yeah. So I apologize. Actually, that was kind of well, because you guys had QGIS, I actually didn't worry about it, but this map should have a label contour interval. I'm sorry, and even a few contour labels. But yeah, so it must be 0.5. So it's again another thing that's level of detail defined, Christy, because if you have too high of a contour interval, not only might you blow up the computer, but all you'll see is contours, right? So you want to kind of find the right contour interval level that is sort of suitable for the data quality, but also suitable to not distract you in your mapping. So this is this data set is called the B4 airborne laser scanning data set, had about 4 points per square meter. And so it can kind of make about a 0.5 meter per pixel digital elevation model. And so we can produce contours maybe similarly up to about 0.5, but if we'd go finer, it might not be meaningful, and maybe a meter is better. But always, people should be careful because you can definitely crash your machine if you draw a cajillion contours, and it might be kind of unnecessary.
All right. Do you
So
want to
let
go
me
to
just,
the answer or like the next?
yeah,
Slides are
thanks.
important still.
I think so. Let me just, yeah. So yes, you had a slightly larger polygon, but in the interest of time, I just mapped the center. But hopefully you did more, because again, there are other things like and I'll show you. There's another little tiny fault here that we should keep our eye on. So, okay, so here's the interpretation. So this is me again sitting at my desk doing something quick. So here's the landforms that we can interpret. So the red is the fault zone, and it's pretty continuous, although going through this lighter blue beheaded channel area, I think it's discontinuous. And this is a little bit of a mapping style thing for faults, like how continuous you draw them, which means they might have to curve versus do you break them, let them be discontinuous and step. And if there's evidence, either way, you have to follow that. But if you don't know, you can see like I'm sort of stepping this fault down as opposed to curving it. And probably maybe curving it's better, but that's the way it looked to me. So there's a beheaded channel here, which is important. There's a shutter ridge there with actually a sag pond right here. There's this big beheaded channel that's in light blue. There's an active offset channel here in the purple violet. There's a trail and a road. This old fan, which is a little hard to see, is this feature here, which you kind of see in the bowed contours. And then there's a younger fan below. That's the thing that Rich and I talked about. And so why is the blue channel not connected to the active channel? Because it's sitting higher. If you look at the contours, it actually sits about 5 or so meters higher. It's beheaded. That's literally the beheading. But what's important is that channel, the light blue, connects with that little bench, which is a fluvial terrace. So this, I'll show you in a second, is called the high channel alluvium. It relates to a former history of this channel. So when the beheaded channel formed, when it was abandoned, the active channel cut down by several meters, abandoning that light blue surface. So there's a trail, and then the scarp over here, and there's little offsets are real. They're interpreted as offsets associated with the last few earthquakes along the San Andreas here. So magnitude 7.7 to 7.9. So here's the, so now I'll just finish really quick. So here's the like answer from Professor Carey C. from his PhD, and then this was published in 1984. And this, so what you guys did, which is really important to remember why you might have a slightly different answer, is you only did this remotely, whereas he spent, you know, days and days in the field. He did augering and everything here. But, and so the colors, I'm sorry, they're not consistent, but the light orange is the active channel. That's he called the HL, I think it's the lower channel alluvium. And then the dark red is that beheaded channel and its continuity with other material and other landforms in the upstream zone. And then this PY is a alluvial fan actually that he identified that's part of the offset story. That would be was hard to pick out geomorphically, but it's right in the middle here. And so that's, you wouldn't necessarily expect to get it, but he did a bunch of auguring to look at the stratigraphy there, and also dug a bunch of trenches, which you guys didn't have a chance to do. So here's the interpretation of this site. So the original alluvial fan is about 19,000 years old. So this is known by radiocarbon dating, a material collected in those trenches. And so there was aggradation. So I've always interpreted this as like last glacial maximum, high sediment flux coming out of the mountains above, aggradation, but then faulting begins, and maybe the fluvial regime changes. And so we incise first at about 13,250 years ago and make that big fan deposit. Actually, sorry, we make the fan over here on the right, and we incise the Wallace Creek incises 13,250 years ago. About 10,000 years ago, that's when that beheaded channel forms, and it gets offset until 3,700 years ago. We know this because there's a big, my light blue fluvial terraces and his HH, the high channel alluvium, are dated. And we know when that thing was abandoned at 3700. So one night there must have been a terrible storm, and boof, it abandoned and cut a new channel. 3700 years later, we're at the present state. Sometime in the future, big storm, we're going to abandon it again. So a little bit more work. This is something I did, which is maybe kind of complicated, but I show how that scarp is exposed progressively. That's why the valleys kind of are deeper as you go to the southeast, and the scarp is more inclined, because the little shutter ridge that we mapped was slid along and it exposed the entire scarp starting actually 30,000 years ago. And so then I go through the story here and progressively develop the things. The main thing is that fan, that PY fan that's green on his map, actually comes from some of the drainages that are to the southeast and not from Wallace Creek itself, because at that time, at 13,000 years ago, this PY fan was accumulating, but Wallace Creek was going out through the first beheaded channel that's next to that that shutter ridge. So this little thing right here doesn't seem like much, but this was 13,000 years ago where the active channel was. So that's the 13,000 year offset of the channel, because the fan, the PY fan, which is here, actually initiated from over here. So this is the beauty of the C work, was this putting together multiple pieces of evidence to demonstrate the reconstruction. Okay, just a couple seconds more to finish the story for you guys. So that's that. So that story, so the C and John story, so this is time versus offset. So that comes up with a 33 millimeter per year slip rate. In later work that we recently published, we came up with 36. We kind of validated it, that this is a pretty solid slip rate. It's a plate boundary rate. And other work we've done at different time scales show it looks like it's fairly steady. So the slip rate hasn't changing. And so then this is my final slide, which is just to show the spectacular topography. So this is a world famous piece of strike slip faulting. On the left is the Wallace Creek complex that you guys have experience with, but further to the southeast is another entire amazing complex that's called the Phelan Creek site. And you see this Y channel is offset from about 6,000 years ago to these two channels. And this is the other key thing just to show you guys is, when we talked about sag ponds, mostly we're talking about geomorphically defined troughs that are just from kind of the juxtaposition of topography. But this one actually has a real tectonic sag right in here, which is defined by a right step in this right lateral fault zone. So this feature here is a true kind of step over that makes a sag pond that's actually a tectonic sag pond. So this thing goes down here and these sides are both up. Okay, so that's my story. I could talk forever about Wallace Creek, but I don't want to delay the lecture anymore. So maybe, yeah, 11:05. I went to let's move on.
You have a question, and then let's move on.
Yeah, could we go back to the contours on the PowerPoint?
Yeah. Screen to share. You guys see it, right? Not my other screen. Is this it?
Yeah, that will be fine. Okay, so that's not the best spot, I think, but like there was a bunch of channels or drainages that were completely stopped at ridges, and I was wondering, how would you call them? Are they beheaded, or they are just blocked drainages, or is there a term for that?
Well, so these are kind of normally behaving channels on their upper ends. So we wouldn't really call them beheaded. They just have had their lower ends cut, or they're they're not really continuous downstream. Whereas these ones that I mapped here, these are really truly beheaded. Like they, once had greater continuity, but they've been cut by faulting. So those are the beheaded ones, just like this one here was cut by faulting and by incision to the modern channel. So usually beheaded means the downstream end is disconnected from the upstream end, but we really only call the downstream one the beheaded one.
Okay, but then like it was more of a general question. So I was just wondering if there was a term for a channel that is blocked by fault and that is non-continuous afterwards.
Well, you could just say it was dammed by a shutter ridge.
All right, thanks.
Yep.
All right, let's go on because we do have a few more things today. Rachel? And then
yes,
I'd like at least 5 minutes at the end.
okay. So if you guys still have any questions to go, like feel free to reach out to us after the lecture too, and we can talk more about Wallace Creek. But we're gonna continue on from the GIR lecture on Tuesday. And so this is gonna be kind of a slower walkthrough, trying to use the shape files that we've created that you guys are gonna use for the mapping assignments in the future. And so I'll share my screen. So you'll locate them on the website and we'll walk through slowly. So if anyone isn't up with the rest of the class, just let me know and we can slow down. But you're gonna download the fault confidence and geomorphic indicator ranking shapefiles. And so this is gonna be a zipped file. It includes the fault shapefiles, the GIR shapefiles, and their style files. And so the style file is just like the saved symbology and layer definitions that we've set out. So we'll want to have those in the same folder, but just download that and store it in a known location on your computer. And once you've downloaded it, you'll want to open up QGIS into an empty project so we can try and pull the shape files down and make sure they're imported correctly for everyone. So is anyone not up to this point yet? Cool. I'm gonna assume that everyone has it up on QGIS. And so the next step is to locate the shape files where you've located them on QGIS in the browser. And so once you've located them, you can click each shapefile and drag it down into your active layers. I'm doing it on the Wallace Creek base map just to show an example. And so if you do drag them down, sometimes it'll already apply the style file. If it doesn't already have the style attached to it, you can load the style file into it. You can do that by double clicking on the layer, going to symbology, and at the bottom, it's going to say style. You can click it and load the style. It'll be located in the same folder that the shape files are located in. So you can click browse. It'll have the same name. You can double click it and load it. And if it's loaded correctly, it should have this symbology. And the same goes for the GIR feature as well. If you double click it, it should have this style file. If it doesn't, you can load it same way, and then you're good to go. Does everyone have that up so far? Cool. And so when you start mapping, you're going to want to do the geomorphic and the morphologic mapping first, like we talked about. So you can either do that on a separate application if you'd like to draw them out. I did like a quick version of it just to show that like you can mark out the drainages, the ridges, the road that Ramon was talking about before you do the geomorphic indicator points. And so when you are finished with all the geomorphic mapping and you want to start analyzing the surface and assigning some of the geomorphic indicator ranking features, you can edit it by going to the top, toggle editing, and then you'll click add point feature. And so wherever on the map you'd like to, I'll choose a random spot, wherever you'd like to add a feature, you'll left click and it'll bring you up to this GIR feature attribute table. So you won't have to worry about the ID, but the feature is where you're going to put the symbology in for the GIR. And I'll show you guys, we have this up on the website as well now. It's the Geomorphic Indicator Ranking System GIR table. So this is going to be a comprehensive tool of all of the inputs with the descriptions, the justifications as the fault indicator for all of the features that you might map in the mapping exercise. And they are separated by what kind of faulting you believe the feature is resulted by. And so when you put the feature name into QGIS, it'll be this 4-letter or 5-letter symbol. So if we go back to here, it is capital sensitive. So you'll want to make sure that everything is capitalized when you're entering it. So let's say I wanted to map a beheaded drainage in a strike slip system. So I'll put strike slip BD. You can always refer back to the table to find the correct symbology. But if you plot it correctly, it should display as a white circle. And if everyone wants to try that, you could just do SSBD. So try and plot a circle, and if it doesn't plot correctly, just give a shout out and we can try to fix it.
Rachel, can you also show them how to display the label too? Is there an abbreviation or something that you can see in some symbology that you can
to have it, to have the dot?
To say BD or to say BD or something, you know?
Yeah, the best, the way that I've been doing it so far is if you ever want to go back to the dot and say like, what was that label? It's just a white dot. You can click on it. So it turns yellow, you know, if you've selected it, and open the attribute table at the top toolbar, or you could press F6 and it'll highlight what the input was. So I know that that highlighted dot was the strike slip beheaded drainage.
We made it so that all the symbology appears with a white dot. So we thought it was easier to do this than to have each different landform have its own color or shape.
Yes, and while everyone's trying to add a circle with any symbology, I'm going to help Ian run back for where we added it. So you'll just find it on the left side in the browser, wherever you've located it, and you can find the shapefile, click it, and then just drag it and add it to the layers. If the style file isn't already added to it, you can double click, go to symbology, and at the bottom with style, you'll load the style found in the same folder. I think there might be a way to add the labels to it. We wanted to keep the maps to be a bit simpler, But if you want to make a map at the end too for uploading or to help count, you can add labels when you make the map too. Oh, edit, you'll click on the layer and then up in the top toolbar, there's a pencil and it says toggle editing. So when you turn that on, the rest of the tools will be clickable and you'll hit add point feature to add a GIR indicator.
Can you show how to delete a point?
Yes. So if I wanted to delete the one I just made, I can go to select features. You'll have to make sure that the layer is activated of the feature you want to delete. And you can either draw a box around it or click it. Once it turns yellow, you know you've selected it and you can hit delete. Yes, you do have to turn editing off. As I map, I like to save layer edits. It's the button right next to the pencil pretty consistently. But when you're finished editing and you'd like to save the document, you can toggle off the editing and it'll make sure that none of the other features that you've plotted up until that point can be changed or moved.
Can you show how to save the edits to the shapefile too?
Yes, yeah, instead of the
And
project.
how that is,
yeah,
different than saving the project, because this is
yeah.
critical.
If you want to ever just save that layer and make a new shapefile that encompasses all of the lines and points you've done up until that point, you can right click on the layer, go to export, save features as, and then it'll bring you up to this box. You can give it a unique name if you wanted to call it Wallace Creek GIR, save it into the same assignment folder, and then you're good to go.
Also, if you're editing it, then once you edit, you'll get a kind of a gray box that will let you save it. Right, Rachel?
Yes, sorry.
We get like a box kind of somewhere around there that's gray.
We had a question from class here at UNR. So you save your layer as a layer file, but if you save if you just save the project, if you save your QGIS project, does it save everything that you've done in that layer that way too, or do you have to individually, save the layer file when you're done also?
The layers, I think if you just hit save project, the layers will be saved into the project file, the .qgz. But if you ever want to separate the layers away and retain all of the information along with it, you'll want to save the feature as separately from the project file, because the layers will still be in the project with the updated features, but to separate it out and save it to include everything, you'll do save the feature as.
So when you are saving, like when you toggle it off and to save your edits, that's like saving the edits to with the shape file that we created them off of. Want us to save our new edits into a separate new shape file? Like, I guess that's what I'm thinking about.
I couldn't quite hear her, Rich, if you don't mind repeating her question.
You want to yell? Just come up and express closer to the microphone.
Hi, sorry. So when we're saving like our edits that we just made off of the GIR feature shapefile using like the button next to the pencil, that is just writing our new edits to that GIR feature shapefile. But do you want us to like write them to a new shapefile, like a separate one?
No, you can save it as this, just like in the future, we'll be wanting to have you guys just send us the shape files for that. So that's when you want to like save it separately to a new folder. It's fine to keep the shape files saved as however, but whenever you want to like export it separately away, it's nice to have a saved feature as, because it keeps it separate and any changes you make on the layers included in the project won't be affected by the one that you've like exported and uploaded.
Okay, cool. Thank you.
I think of like these ones as like always the active ones. If you ever want to save it with what you have at that moment, that's when you'll use the save feature as, but it'll continuously update in the original file as you add mapping.
Can I just restate, I think last class some people had trouble with this. So if you click there, that's where you save your QGIS project. And so that will essentially make a QGIS project file that can locate all your shape files as long as you don't move them. And so that's an easy way to open up all your files. But if you want to save any of the line work that you do or these points that you enter, then it's absolutely critical that you click that save, which will save your GIS shapefile. Just clicking this one here does not save any of the line work that you're working really hard on doing. So just, keep that in mind throughout the semester.
Okay, so unless anyone hasn't gotten the white circle down, we'll move on. And you'll see next to here, there's a gray circle. So when we start to map our modifiers as well, the features that aren't strong enough on their own to be mapped as an indicator of active faulting, but if they are found near features that indicate active faulting, we will map them and count them. They do have a separate symbology as well. There's going to be a table at the bottom that can show you all of the modifiers that we talked about, some things like the vegetation lineament, landslides, saddles, there's a bunch of them, but same way to map that one. You'll do all capital letters, and let's say that's a vegetation lineament. So if it's plotted correctly, it'll plot as a gray circle. If it isn't plotted correctly, you do something wrong with the letters or the font and it's not all capitalized, you'll know. Let's put some lowercase in there. It'll plot as a giant red star, so you know that there's something wrong with the input. And so after you are done mapping all of your GIR indicator features along with your geomorphic and morphologic mapping, you're ready to draw your fault line based on all of the available evidence that you've mapped up to that point. And so to do that, we won't be using the fault confidence ranking just yet. We're going to be making our own shapefile to draw a simple fault line. And so to do a new shapefile, we're going to go up to the toggle bar and it's going to say new shapefile layer, and we'll click that. It'll bring you to this window and it'll say file name. You can name it simple fault for now. And you'll want to locate it into the same folder that the rest of the files are for the project. And so you can browse and locate it that way. And I'll give you guys a sec to do that. And so you'll be able to see the pathway that you chose into the file name. The geometry type, we're gonna wanna make a line, but anytime you make a shape file, you can choose polygon, point, line. This is gonna be the same process on how to make a new one. Make sure that the coordinate reference system is the same that you've been doing the other mapping in. And then you're good to go. You can hit OK. I already have something called simple fault, but this is what it would have looked like right there. So the one I made previously was called simple fault for Wallace Creek. You can double click on it to change the symbology to whatever you like. And when you're ready to start mapping your fault line, you'll do it in the same way. You'll go up to the toggle editing. You can add a line feature. And I'm going to just do a really rough line of where I think the fault trace is. And you don't need to put an ID for this one. And you'll notice that when I mapped the geomorphology, hold on. QGIS might crash on you sometimes. So when I mapped the geomorphology of the area, it expanded far beyond where my geomorphic indicators were. So you'll want to only map what geomorphic features are indicative of active faulting along the fault trace, because that's going to be what you're counting towards your feature ranking. I'm going to pretend that this is a fault now.
So yeah, Rachel, QGIS did quit. That does happen infrequently, but sometimes. Don't worry, it is best just to restart it.
Which is why it's good to save quite often as well. But let's put a line where we think the fault is going to be roughly with our indicator rankings. And so if we're all up into this point, I'll show you then how we segment out the fault to then segment it into 1 kilometers. So then with anything that falls into that 1 kilometer zone, that's going to be counted to find the final fault confidence ranking.
Let's wait a second and give you a couple minutes for questions. Yes, so as Tamara says, you can have a plugin which auto saves. Never used it, but maybe worth trying. And if you go to the top toolbar, you'll see plugins. I did want to just quickly say, so we saw Rachel was putting in these dots for the different landforms to mark them, and then had that capitalization. It's really important that you do put that capitalization correctly and that you don't get that black or red star. And the reason is that after this semester is over, we're going to be doing analyses, working with PG&E on your maps, and we need to be able to really quickly know what landform you mapped adjacent to the fault. And so using that consistent capitalization and lettering is really important for us being able to use your maps in further analyses.
Yes. So has everyone been able to make a new shape file? You can make it red, draw the general line of the fault.
So we're just
yes. Yes, and then I also did make a video last night that like condenses this into a 10-minute video from like step 1, step 2, step 3, step 4. So I have that on the class videos too, but I might breeze through to the next step just to make sure Chelsea has time at the end. But I have it all on this like nice video that'll be on the class website after the class ends. But you're gonna first do geomorphic mapping, then indicators. We'll draw the simple fault line. We'll start to break it up into the 1 kilometer sections, which I'll show right now, and then we'll go on from there.
And we're gonna build these tools slowly in the homework assignments.
So I have kind of annotated on the side here what the segments look like. And our mapping area was a bit smaller. So we only had like about 1.5 segments. So you can use the measure tool on QGIS to measure out one segment. You'll go up to the measure line button in the top of the toolbar, and you can start on one end or the other of the fault trace and just map it out to 1 meter so you know where to stop your segment. So about right there. And so every geomorphic indicator feature that we've mapped that falls within that segment is going to get counted towards the segment score. And so that annotated here, I just use the symbology to save some space, but along this trace, just kind of as an example, we had a strike slip offset drainage, which as on the it has a score of 4. There's no other way that that could be formed without any active faulting. Some beheaded drainages, a scarp. We have the shutterage at the far end of the mapping boundary, a morphologic element that's right near the beheaded drainage, that ridge, and then an alignment of the, I guess like the lineation or the scarps toward the middle. So if you want to add all those together, you get a segment score of 20. Then we go down to the second one where we just had a beheaded drainage, and on the base imager, I saw a vegetation lineation. So that would be a score of 4. And to kind of give you guys a better idea of how it would work with a longer fault trace, I included some like random segments of different scores. So let's say you had another segment that had a score of 15, and then 2 segments that had just a score of 2. So maybe there wasn't really any indication of active faulting with it other than the fact that it was along the same strike. So after you've segmented everything and added the indicator features within each segment, and you get your segment score, you're now going to have to translate that into your fault confidence ranking. And so what I normally do is the highest one would mean that it's probably the strongest, and based off of if it's primary, secondary, but I normally have the highest score be the strongest, the lowest score be uncertain. And then it's up to you guys to kind of determine what boundaries you want to set for the distinct, the weak, the strong, like what number or what amount of evidence towards the fault trace would you kind of assign the rankings in between there. And so once you have decided on your segment scores and the final confidence ranking, you can go back to your QGIS, and we'll use the fault confidence ranking file now. And so in the same way that we did with the GIR, we're going to toggle the editing on for the feature. And we're going to add a line feature. It's nice that we've already drawn out, and you'll want to do this in more detail than I did just now, because you are going to follow pretty much directly on top of your old feature. And let's say, I think the other one stopped like right here. And so when you right click, it'll bring you to the input table. Again, we won't have to worry about the ID, but P or S is where you're going to want to distinguish between primary or secondary. I'm going to say this is a primary fault, and you can refer back to the GIR lecture from Tuesday with the slides of ways to help you distinguish between primary and secondary when you're mapping. But you also feel free to do some like research on your own about ways that other mappers help distinguish between the two.
Well, we'll talk about differences in primary and secondary faults later as well. So we'll have some of that to go on.
Okay, cool. And again, it's capital sensitive. So if you don't put is the capital P, capital S, it won't plot correctly. And then quality is where we're going to type in 1 through 4, the ranking that we've assigned. And in the same way that the GIR is scored, 1 is going to be the worst, 4 is going to be the best. So 1 is going to plot as an uncertain, 2 is going to plot as distinct, no weak, and then 3 will plot as weak, and then 4 will be like the strongest one. It has the most geomorphic evidence assigned to it. So let's say I wanted this one to be a 4 because it had the highest score, it had the most geomorphic evidence assigned to it. And so once I plot it, I can hide that to show you that it'll plot as a strong primary fault. And then if I wanted to maybe have it be a weak secondary fault to show that that would look like, it'll be a dashed line, the same symbology that we have right here for you. And I'll give you guys a sec to try and make a fault using the file.
So Chrissy asked a good question about eyeballing confidence features. And so we've developed this approach in a way to standardize the confidence ranking so that they're defendable, but also ideally repeatable by different mappers. We're also going to ask you on some of the work from this semester to eyeball or give the confidence ranking based on your geologic intuition. And then we're going to be looking at comparing this numerical ranking versus the geologist's intuition.
And I would spend some time too, because I know we're also very new to the geomorphic indicator features for faulting. We're familiar with the morphologic, but when we're trying to determine whether or not is that an offset drainage, is it not an offset drainage, I would go back to the student GIR table and just take some time to read over the descriptions of everything. You can also try and look up images of some of these features to see what they'll look like in the landscape. But it also is something that takes some time to get used to, because I still find features that I misidentify. But the idea is that that feature should come from all of the evidence from the morphologic and geomorphic mapping to then find that indicator feature.
All right, we can have like one question, but I do want to briefly discuss the next homework assignment.
Yeah, and that was the final point too. So I'm still available after class too. If anyone can't get some of these shape files to work, we'll be working them throughout the semester. So hopefully it gets a bit easier as the assignments go on. How do you keep the segments for the measuring tool? Yeah, so you can do it one of two ways. Sometimes I will measure it and then look for some kind of point in the landscape and be like, okay, it was right before that drainage. Or another way to do it that I've done before is to make a new shapefile that's a simple point feature. And you can do it that way. So if you make a simple point feature, you can call it like 1 kilometer segment spacing. You can add it directly at the point where the end is. So then you can see it more clearly in the surface where it is. Like I think that was the end of the first one. So after you measure it, you can add the point feature. And then you'll know that's where to stop for the first segment. And you can do that for the entire trace.
All right. So you have the next mapping assignment is going to be due on Monday night in a week and a half or so. And just wait 1 second. Hi. Barn, can you come, please? He's coming. Okay, so yeah, you'll find the assignment instructions right here. And then you're going to be downloading this digital terrain model or DTM of Bainbridge Island. And this is just outside of Seattle. And so We were previously in California, but now we've moved north along the coast. So you might hypothesize that we're no longer in a strike slip climate or environment. Perhaps we're in a different type of tectonic area. And so this assignment is going to be focused on Bainbridge Island, which is here just across Puget Sound from Seattle. So here's the island. You might at this scale say, there's no faults, or I don't see any faults. And so the assignment that you'll be doing, you'll be working on mapping from a digital terrain model, which is from LiDAR data. And this data is critical for being able to see past or through the trees, be able to see what the bare earth landscape looks like. And so when you're mapping, I just want you to appreciate what you can see from the LiDAR that you can't see in this imagery. And so the DTM that you download from the course webpage is going to be the southern part of the island. Do not get the DTM for the entire island. We just want you to map on the DTM that we provide. And so we're going to be focusing first on mapping the morphology like you've done for this past assignment. And then the next step is to map the geomorphology. And so these morphology and geomorphology mapping can be done using shape files on QGIS. You can also take a screenshot, map on PowerPoint, Illustrator, or even print. That is up to you. But then the technology part of this assignment is to use that point file that Rachel just showed you to label the geomorphology. And so think about here we're in a very different climate than the California desert. Don't want you to look anything up. Think about what you know in Seattle. Perhaps there were glaciers. What's the impact of being an island? So yeah, just keep that in mind as you're doing the mapping. And on Tuesday, we'll be discussing compressional tectonics, and in particular, why there's faults in Seattle and how this relates to the greater tectonic boundary. So I'd be happy to take any questions. Got one more minute of the class.
Just a historical perspective, the LiDAR data up there at Bainbridge was one of the first LiDAR data sets used for paleoseismology, 1998, I believe. And basically it was the first time they discovered active faults in the Seattle area using the LiDAR. So, and they've since identified a whole handful of other faults with LiDAR data in Puget Sound.
You'll be getting your first assignment back in a week from now, and so you'll have about half a week after getting that one back before the next one. But we do strongly suggest that you start before then.
And
Yeah.
There's no mapping polygon on this assignment. You're going to be mapping the full extent of the DTM.
Lots of trees, yes. And the LiDAR that you have is from, I think, about 7 or so years ago. So it's updated from that first data set that Rich was talking about, and probably does allow us to see through the trees better and see the fault at a higher resolution than the earlier data set. Although yes, the earlier data set was critical for seeing faults in the Pacific Northwest.
And there's a fill-in observations on the entire polygon that's provided, is that correct?
Sorry?
Fill-in observations on the entire polygon that was provided on the entire DTM?
On the DTM, yeah, there's no polygon, and so you're mapping the entire DTM, not the entire island. Do not go get data for the rest of the island. We want you to focus your time on where we have the DTM.
Awesome. Thanks, everybody.
All right, we're at the end of class. Thank you.
All right, we'll talk to you soon.
Okay.
Yep.
Rachel, and I had a couple questions about our approach. And maybe Ramon, if you had like 5 minutes, but if not, Slack's good too. So I actually didn't quite know that we were gonna go through all of the like scoring.
You want to shut the recording off?
Thank you.